All right, so we are doing complex numbers. And I say they're imaginary. They are imaginary. They have an imaginary part. We say they're not real, but you actually can do a lot of math with them. They model a lot of things that happen. They're used a lot in physics to model things. So it's not like they're fake. I don't want you to think that they're fake. We define it though. An imaginary number, let's start there. An imaginary number is basically a number that, when it is squared, gives a negative. That's what we define it as. So basically, we're going to say that number is I. That imaginary number is I. If I square that, I get a negative. In fact, I square it and I get a negative 1. So we're going to start there. I squared is negative 1. So if I take the square root of this, I get I is square root of negative 1. So it's going to be with imaginary numbers that I can actually do the square root of negative numbers. So if I wanted to know the square root of negative 4, like I alluded to earlier when this was coming up in our quadratic formula, we're going to simply say, split this up into 4 times negative 1. Now I can do the square root of 4, and I have the square root of negative 1. We just defined that the square root of negative 1 is I. And then the square root of 4 is 2. So this answer is 2I. Now you don't need to show all this work. I'm just showing you where it comes from. So if I wanted to do the square root of negative 25, well, I'm going to say, well, the square root of 25 is simply 5. And I recognize that because I have a negative here, that I'm going to need an I for the imaginary number. So the imaginary number is a number defined that when we square it, we get a negative. Now, I can't think of a quote-unquote real number. Like, I can't take negative 1 and square it and get negative 1. I'd get a positive 1. So that's why we define it. We just use this letter to represent that number, whatever it is, that if I square it, I get a negative 1. Okay? Well, that's going to enable us to do a few things that we weren't able to do before. So for example, if I had x squared minus 25, and I asked you to factor that, we could easily factor that because notice our middle term is what? Yeah, it's missing, so it is 0. Okay, so when we factored that, we did this. There's nothing in common, so I have x times x, and then 5 and 5, and then I subtract and I add. But then when we had this, so we can always factor the difference of perfect squares, but when we had the sum of perfect squares, if I had this, there's no combination here. If I did x minus 5 and x plus 5, well, I'm going to get this, right? So that doesn't work. And if I had x plus 5 and x plus 5, well, then if I multiply that out, I get x squared plus 10x plus 25. So does that work? No. And then if I did x minus 5 and x minus 5, if I multiply that out, I get x squared minus 10x minus plus 25. Does that work? Does that give me this? No. So none of these possibilities even work. So I can't factor that until now. Now I can factor it. I can say x and x. I can say 5 and 5. I can do my minus and plus, but now because I have that plus there, I and I, imaginary numbers. So we're going to see why this works. I'm going to show you why we'll be able to do it this way. But likewise, if I had x squared minus 16, I can factor that to x minus 4 and x plus 4. So now, if I had x squared plus 16, before you could not factor that, now you can. You can say x minus 4i and x plus 4i. And again, I'll be showing you here shortly why that works. But let's go back to, I'm kind of getting ahead of myself here. Let's go back to what a complex number even is. Alright, so I talked about imaginary numbers. Imaginary numbers, this whole I squared thing. I squared equals negative 1, and I equals square root of negative 1. What if I had I to the 30th? For some reason I had that. Well, let's see if I can get some other i's on my table here. I'm going to want 4 of them. So I is root negative 1. I squared. So if I squared this, the root goes away, so I have negative 1. Well, let's get a 3. I to the 3rd. So down here, I'm going to show you how we figured this one out. If I start with I to the 3rd, I could split that up using the rules of exponents to I squared times I. Well, I squared we already defined. I squared is negative 1. So, I cubed is negative I. The next one we need to know is I to the 4th. And you're going to have to memorize these 4. So I to the 4th, let's figure out that one. Like I to the 3rd, I can split that up, and I guess I'll do it over here. Okay. So like I to the 3rd, and I split that up, I can take my I to the 4th, and I'll split that up to I squared and I squared. But what is I squared? Negative 1. What's this I squared? Negative 1. What's negative 1 times negative 1? 1. So we need to memorize this table, or at least be able to produce it based upon these first two. These first two are the most important, because from them I can get the other ones. So when I'm faced with this I to the 30th, well, I want to reduce it down to one of these. And the most powerful one to use is actually I to the 4th. Because I to the 4th equals 1, so I have a bunch of 1s in here. So here's how I can think of this. Here's one way to do it. I could go I to the 4th times I to the 4th times I to the 4th times I to the 4th. Now let's see here. That's 16, 20. This is kind of getting tiring, right? But basically, 1, 2, 3, 4, 5, 6, 7. So 7 times 4 is 28. So that leaves me with 2 more. And all of these equal how much? Each I to the 4th here is actually a what? Is actually 1. So I have 1 times 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 1, all the way down. Okay, I have too many 1s. 1 too many 1s. Times I squared. And what's I squared? So this equals negative 1. Now luckily, I don't have to do it this way. I can do remainders. So if I take 30, and I want to get out all the I to the 4th, I simply divide that 30 by 4. And I get 7, and 7 times 4 is 28. I subtract, and actually, this is remainder is what I want. So this is all the I to the 4th that are in there. That leaves me with an I squared. And I squared is negative 1. And so I can get there a lot faster. I'm going to do 3 more of those. They aren't as common of a question as the rest of the things we'll go over. So let's say I had I to the 65th. I want to take out all I to the 4ths. Because I to the 4th is simply a what? A 1. So I'm going to take that 65. That's all I care about, that exponent. And I'm going to divide it by 4 because that's going to get out all the extra I to the 4ths. So I see, by doing this, that I have 16 I to the 4ths in there. That gives me 64 in the end. Okay, I did my long division there incorrectly. 1 times 4 is 4, right? Subtract, bring down, and then 6. 6 times 4 is 24, subtract. Okay, so whichever, doesn't matter. But in the end, I get a 1, which means I to the first power. Done. That's simplified. If I had I to the, let's see here, 23. All I care about is this exponent, and I'm going to take out all the I to the 4. So I take 23 divided by 4. I get 5, subtract, and my remainder tells me how many i's I have left. So I have I to the third left, which is, from our table, negative I. We need to memorize that. So that's negative I. So that's my answer, negative I. One more. Let's say I had I to the 18. Again, I just care about that exponent. 18, I'm going to divide it by 4 because that's going to tell me how many i's to the 4th I have in there. So 4 times, I get 16, subtract, I have 2. So I have 2 i's left, so I squared. But I squared from our table is simply what?
Negative 5.
Negative 1. I squared is negative 1. Okay? And in fact, if you remember nothing else, remember this. I squared equals negative 1. That is the most important piece of all of this, is to remember that I squared is negative 1. Very, very important, because you're going to need that to be successful at the rest. Alright, well, what can we do with these? Okay, so that's our review. I'll get rid of that review. Let's now talk about a complex number. A complex number is a real number with an imaginary. And they have this form. A, not the same as A from vertex form, plus or minus B, I. This first thing is our real part. This thing is our complex part. So this number is complex. Now, I want you to, this is a very, very, very important distinction that you need to recognize. How many numbers are here? How many numbers are here? Just
2.
Okay, I heard 2. And why do you say 2? Because you see a 4 and you see a 3. Okay? This is one number. And that's the confusing thing about complex numbers to keep in mind. This is representing one thing. It does have 2 parts. That's true. It has 2 parts, but this is actually a single number. A complex number is a real number together with an imaginary that together form one number. So this is one thing. Now, like with all real numbers, complex numbers, we can add, subtract, multiply, and divide. We can do all those things. And it's not as difficult as you might think. Well, before we get to add, subtract, multiply, divide, let's represent this number. Let's graph it. So normally when we graph, we have x, y, right? Not anymore, not for complex numbers. This is real, and this is imaginary. So if I wanted to graph 4 minus 3i, we're going to basically consider this our x component and this negative 3 as the y. But what I want you to emphasize, even though this is in a two-dimensional plane, this represents one number. Okay, so 4 minus 3i is right here. 4 negative 3. What if I wanted to graph negative 2 plus 5i? X, y. So it's important to get your complex numbers in the right order. So that is going to be 1, 2, 3, 4, 5. That's right here. That's negative 2 plus 5i. Well, what if I have negative 4 minus 6i? I hope you're seeing all you do is graph at x comma y, basically. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Any questions on how I'm graphing these?
What would be the point of actual graphing?
Well, to do what I'm about to do. Alright, so I've graphed each of these complex numbers. Now, from real numbers, I don't want you to write this down. What's the absolute value of negative 6? And what's the absolute value of negative 5? What's the absolute value of 10? 10, okay. And let's review. I do want you to write this part down. I'll get rid of this. Okay. Absolute value is distance from 0, right? So that's why we ask the question, how far, we're asking the question when we do like absolute value of negative 5. We're asking how far is negative 5 from 0? And we say 5 units. We can also find the absolute value of a complex number. Okay. This is called magnitude. That's the word that's usually used. Magnitude. So if I want the distance from 0, one of our numbers was 4 minus 3i. I'm finding the distance from 0 of this. Alright? This is why I graphed it. Here's 0, right? Here's the distance from 0. You with me? That's a big slanty line, right? But if I connect this, what have I made? A right triangle. How long is this side? And how long is this side? So the question is, how long is this side? Do you think of a way in a right triangle that you can find this missing side?
A squared plus b squared.
A squared plus b squared equals c squared. This actually is the way that you find. See, when we have just a real number, absolute value is pretty simple. And I don't know how I have control shift up there, but that's very annoying. That's going to mess up everything. So a squared is 16. B squared is 9. Add those. And then what do I do? Not square it, square root it. So C is 5. So this is 5. So what's our magnitude? 5. Now luckily there's an, does boil down to Pythagorean's theorem, but the magnitude of any is going to be the square root of a squared plus b squared. That's going to be our magnitude. So – when I have negative 2 plus 5i, negative 2 plus 5i. Well, that's up here, right? The distance from 0 is this. You with me? So I can complete my triangle if I'm doing it on a graph, right? This distance right here is 5. This distance right here is 2. This right here is my magnitude, my distance from 0. It just happens to be in 2 dimensions. So I'm going to do square root of a squared plus b squared, which is square root a negative 2 squared, that's 4, plus 25, that's square root of 29. So, that was negative 2 plus 5i. That was root 29. Let's do the magnitude of the other one, negative 6 minus 4i. Oops. Or was it negative 4 minus 6i? That's what it was. Okay. Without even graphing, square that, square root it. So 16 plus 36, square root 52. Done. That is the absolute value or magnitude of a complex number. All right, so I said that whatever we can do with real numbers, we can do with complex numbers. So we did the first thing. We found absolute value of a complex number. But we can also add, subtract, multiply, and divide. We'll probably save divide for tomorrow, because that's a little bit tricky. But add, subtract is amazingly easy. So let's say I had 4 plus 2i. So there's my first number, minus, or plus, let's say negative 7 plus 8i. Now again, how many numbers is this?
1.
In this, I'm really adding one number. But the concept to add these is pretty simple. It's just like terms. I add the real part, and I add the imaginary part. So I mean, seriously, you see this on a test quiz, you just combine like terms and you get the answer basically. 4 minus 7 is negative 3. And 2 plus 8 is 10. So negative 3 plus 10i. That is the answer. That little thing in control shift is really bothering me. I don't know why that means something. So add your real part. What do I get on my second example?
Negative 2 plus 2i.
Yeah, negative 2 plus 2i. You might be thinking, wait a minute, Mr. King, there's no 2 parts. Doesn't matter. Okay? This just has a complex part. It just has the imaginary part. It doesn't have a real part, which we'll actually graph that in a minute. So what does this equal? Well, I add my real parts. There is no real part here. So 4. Negative 9 plus 20, 11i. So adding and subtracting these, pretty easy, right? Am I way off? Easy on adding them?
4.
Combine my like terms. These are like, right? That's what I'm doing. Do this one on your own in your notes. For anyone that's interested in physics, you can use complex numbers to do lots of physics problems. And they actually make the physics easier than if you did not have the complex numbers. So we get negative 3 plus 5, wait, not 5i, 11i. Okay, so that being the answer there. All right, so We've done absolute value, and we've added complex numbers. We, of course, can subtract complex numbers. So let's say I'm subtracting these. I would argue that probably you're going to want to distribute this negative and switch it to addition. And that's highly how I'd recommend you do that. You can do it in your head. What's 5 minus 6? And what's 4 minus 10? -6, right? So, I mean, I can do that. But then when I have something that has some negatives involved, or the problem is bigger, I would highly recommend that you simply distribute that and switch to addition. So I copied down the first one. I'm switching to addition, so that means I'm distributing that negative. And I get 8 plus 12i. And now I just do an addition problem. I think it's way easier to switch the signs and add than it is to subtract in my head, especially if I have a lot of negatives. The tendency is to make a silly error. And don't do silly errors on this. Now, those of you with Casios are going to be very happy. Your Casio calculator can do imaginary numbers. So you can literally type this in the way it appears, and your Casio will actually do the imaginaries. The key is actually find the button that is I. We should get 2. I imagine the TI also does it. I just do not know how. So that would be something that you figure out on your own. Any questions on subtracting?
Why did you distribute the negative?
I just find it easier to switch to addition. So I distributed the negative, switched all the signs so I could do a plus instead. If that doesn't make sense, I mean, because to me, I would have to say -6 minus a -8. Kind of confusing, right? So I would distribute that negative and switch to addition. So let's do one more. Do this one on your own in your notes. I don't know why I like 5 this afternoon, but sure. And see what you get there. And look up when you're done. That's what I got anyway. Do we agree? So distribute that negative makes it easier. So we've added, we've subtracted, we found absolute value. Okay, so you have to be able to do those 3 things. The tendency is to forget how to do the magnitude, the absolute value. Adding, subtracting, I generally don't have anyone who forgets how to do that. And sometimes students mix up adding and subtracting with the next one, which is multiplying. I don't know why that happens, but it happens. So just be aware of the operation. So what if I had 5i times 2i? Okay, so that's an imaginary number, complex number with no real part. I'm going to multiply the 5 and 2. So just like usual, I get 10. Rules of exponents, what's I times I? I squared. But we need to recall, and this is very important, I squared is simply what? -1. So I need to, that's going to be a step that you need to remember, especially when you're multiplying. I squared is -1. So 10 times -1 is -10. So when I multiply that, despite it being imaginary numbers, in the end, I just get a basic real number, -10. That doesn't always happen, but sometimes it is fair game. I could have a distributive property where I have 3i out here, and then I multiply it by something in here. So let's see what happens. I go ahead and I distribute that like I think I would if it wasn't even a complex number. So right here, 3i times 5 is 15i, plus 3 times 2 is what? So, and then I times I is what?
I squared.
I squared. But again, I squared is what? Negative 1. So I get 6 times negative 1. Well, what's 6 times negative 1? Negative 6. Now this is backwards. Real part needs to come first. So I move the negative 6 up, and I drop the 15i back. So I get it in the right form, because complexes should be in the form a plus or minus bi. I want the x part first, basically. So we could have it in reverse order. I could have negative 4 minus 9i, and then I could have something over here, like maybe a 5i. So in that case, I'm going to distribute this way. Just like I would if I had x's in things. It's basically, instead of an x, I have an I, and the I is actually representing the imaginary part. And I is just defined as any number that's squared gives me a negative, which is no such real number. So when I multiply this out, I get negative 20i. Now I multiply, what's negative 9 times 5? Negative 45. And then I have, see, I have an I there. So what's I times I? I squared. And that's going to be the trick to all of these, is you get an I squared. And I squared is simply what? So I'm going to switch that sign, and I get 45 minus 20i. Really quick, ask your question.
I'll be right back.
Oh, okay.
I'm going to put the subtotal.
All right. So any questions on those? All right. We are almost done with multiplying. Here's where students always, I don't know, they turn into bonobos. Don't turn into it. Do not be a bonobo. They are not healthy. Okay, so what I find is students will, here, we'll just do the difference. That way you're seeing what I'm talking about. Do you see the difference between these two questions? This one's an addition problem, right? This one is a multiplication problem. What I find many students do is they take this addition problem and they multiply it, thus getting making something that's actually pretty easy, making it unnecessary. Multiplying it's not going to be that bad, but this is way easier. What should I get when I add this? Well, 2 what?
2 minus 5i.
2 minus 5i. Alright, so when I multiply, it's going to be like this. And I'm going to do this down here, and if you remember, there's no need for you to write this, but if I were multiplying those, do you remember I multiplied this times both of those, and this times both of those. So x times x is x squared, x times negative 3, negative 3x, 5 times x, that's plus 5x, and 5 times negative 3 is negative 15. And then I combine my like terms in the middle. So actually, this is going to work out the same way. I'm going to do 5 times both of those. So what's 5 times negative 3?
Negative 15.
Negative 15. And what's 5 times negative 7i?
Negative 35.
And don't forget the I though. And now, I'm going to do the 2i times negative 3. 2i times negative 3 is,
Negative 6i.
and then 2i, here's where the trick's going to come in. 2 times negative 7 is negative 14.
I squared.
And then I times I is I squared. So I keep my negative 15. It's not like anything yet. What's negative 35 minus 6 side? See, these are like, so I can combine them. And I get negative 41i. Right here, what's I squared?
Negative 1.
So that makes this negative 14 actually a plus 14. Now I can combine these. Do you see that these now combine? So it's negative 15 plus 14. And again, you can put this on your calculator and it will do this and it'll actually put the I in. Unless it is overly complex. If it gets What I mean by overly complex, not complex numbers. What I mean is if it's very complicated, it has a lot of pieces to it, it won't do it. It won't do it. But if it's simple like this, it will actually multiply and give it to you. Let's do one more long multiplication. All right, you multiply it. What do I get?
-18
Plus
plus
27.
I.
Don't forget the I. Then what?
Plus 24i.
Minus 24i.
And plus 36
I squared. And then that I squared piece becomes negative, so it's negative 36. I combine those and I get 3i. I have negative 18. And then just work this down. So negative 18 minus 36 is negative 54 plus 3i. Okay? I see that you have homework tonight. Page 255. Which makes, that makes no sense. Here's what I want you to do. I'm going to have to change this up. I want you to do page 253. And you should be able to do numbers 8 to 26 off. Most of them are pretty short. Like, they will take you like only a couple of seconds. And then the rest we'll do later.